Hello, this is Monique Morton, Senior Content Director for Mathematics and Computer Science with Advanced Kentucky, and this is another optimization problem for AP Calculus. Let's read the problem. A rectangular garden plot is to be built along one side of an apartment building. The garden plot will be divided into four side-by-side plots of equal size with parallel partitions perpendicular to the building. What is the maximum area of one of the subplots if there is 140 feet of fencing available to build the garden? Well, this is a case where a diagram will probably help. So let's say here's my building. See, building, right? And we're going to build a garden, right? It's a rectangular garden that's going to be divided into four equal subplots. One, two, three, four. So what we want to maximize, what we want to maximize is the area of one of the subplots. So let's say this horizontal length is x and this vertical length is y. The quantity we want to optimize is the area, xy. Now we need to be able to write the area function, my optimization function, in terms of one variable in order to solve the problem. So let's fill in the diagram with some more information. In fact, all of these vertical sides are y, and all of these horizontal sides are x. I don't need anything along the building because that's going to act as a side in all of the subplots. And I have 140 feet of fencing. This is my constraint, right? This is all the fencing that I have. So if I add up the 4x's and I add up the 5y's, the sum should be 140 feet of fencing. So this constraint is going to help me create an area function in terms of x alone. Another note, maybe we should talk a little bit about domain. I don't really know how to chop up the different values for x. Maybe I don't need to. I know x has to be greater than 0. Let's just say, in light of no other information, that x got to be somewhere between 0 and 140. This is probably a smaller domain than that, but that's what we're going to go with right now. In the meantime, back to my constraint equation. I'm going to solve this equation for y. So y is equal to 140 minus 4x, and I'm going to divide that by 5. So I'm going to write it as y equals 28 minus 0.8x, 4/5, 0.8, same number. And now I can go back and write my optimization as a function, my area function. A of x is equal to x times y, where y is equal to 28 minus 0.8x. Or distributing the x through the parentheses, 0.8x squared. That's my area function. So now that I have my optimization function in terms of one variable x, I'm ready to go about the business of finding out when is this function a maximum. So let's find the critical points, which means first let's find the derivative. A prime of x is equal to 28 minus 1.6x. This is a polynomial, so it's never undefined, but it is equal to 0. A prime of x is equal to 0 when x is equal to 17.5. Set that equal to 0 and solve for x. This might be a good time to use the second derivative test. So let's do that. This is going to be pretty easy. Just take the second derivative. Here's the first derivative up here. A double prime of x is equal to negative 1.6, which means that the second derivative is always less than 0. So I'm ready to write my justification and answer the question. sense, the only critical point is when x is equal to 17.5, a prime of 17.5 is equal to 0, and a double prime of 17.5 is negative. All that together tells me the maximum area occurs when x is equal to 17.5. Now, have I actually answered the question? It wanted the maximum area. I just told you when the maximum area occurs. So the maximum area is a of 17.5, which is equal to 28 times 17.5 minus 0.8 times 17.5 squared. So the maximum area is 245 square feet. The max area is. Okay. So let's go back through our steps again. First, we started with reading the actual problem. And then after I read the problem, I decided I'd go ahead and draw a diagram. So here's my diagram over here. I wrote an equation for the quantity I wanted to maximize, which is the area of one of the subplots. I wrote my constraint equation, by the way, for the 140 feet of fencing available, and that allowed me to write the area in terms of one function, one variable, x. Now that I have my area function, I could go ahead and find the derivative. I only had one critical point. I went ahead and found the second derivative and used the second derivative to justify that at this critical point, and it's important here that I stated that I was looking at the only critical point. That is my indication that I am considering the entire domain, so that this is the absolute maximum and not just a relative maximum. That x is 17 and a half. The first derivative is equals to 0. That's important. It has to be the type of critical point where a prime is equal to 0, not undefined. And the second derivative is negative. That tells me when the maximum value occurs, and the maximum area is 245 square feet. I hope you found this example helpful. I'm Monique Morton from Advanced Kentucky. Thanks.